Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 11, Section 3, Notes all over reactions in aqueous solutions. So today we're going to be talking a lot about net ionic equations. Our world is water-based, and 70% of our surface is covered by water, and 66% of the adult human body is water. So it's not surprising that many important chemical reactions take place in water, what we will call aqueous solutions. So if we look at this equation, we have silver nitrate plus sodium chloride yields silver chloride solid plus sodium nitrate. This is a double replacement reaction, and the equation does not show that. Like most ionic compounds, the reactants and one of the products dissociate or separate into cations and anions when they dissolve in water. When sodium chloride dissolves in water, it dissociates or separates into Na plus ions and Cl minus ions. So if we look at this equation, when it's dissolved in water, silver nitrate dissociates into the silver ions as well. And you can use these ions to write a complete ionic equation, an equation that shows dissolved ionic compounds as dissociated free ions. So when we look at this equation, all we did was we separated all of our aqueous ionic compounds. We broke up AgNO3 to Ag plus NO3 minus. Sodium chloride is now Na plus Cl minus, and it yields silver chloride, which is our solid, so we're going to keep that together, plus Na plus NO3 minus. Now if you notice, NO3 and Na plus are unchanged on both sides. And the equation can be simplified by eliminating these ions because they don't participate in the reaction. So what we will eventually get into and what we'll be able to do is to cross these guys out because they don't participate in our reaction. So an ion that appears on both sides of an equation and is not directly involved in the reaction is called a spectator ion. When you rewrite an equation leaving out the spectator ions, you have the net ionic equation. The net ionic equation is an equation for a reaction and solution that shows only those particles that are directly involved in the chemical change. So like on the last slide, we were able to cross out the nitrate ions and the sodium ions because this is where our chemical change occurred. So we were just left with Ag plus Cl minus yields AgCl solid. In writing balanced net ionic equations, you must make sure that ionic charge is balanced. The net ionic charge on each side of the equation is 0 and is therefore balanced. Here we have plus 1 from the silver, minus 1 from the chloride, so they cancel out to 0, and we have no ionic charge on the right-hand side. So this is balanced out. Consider the following skeleton equation. We have lead plus silver nitrate yields silver solid plus lead nitrate. The nitrate is the spectator ion in this reaction. The net ionic equation is as follows. We have lead plus silver plus the silver ion yields silver solid plus the lead ion. And now this is unbalanced, and it's unbalanced because of the charge. We have a 2 plus on the right-hand side and a 1 plus on the left-hand side. So to balance that out, we're going to put a 2 here. So that gives us 2 silver ions. So now our charges are balanced on each side. But now we need to also balance out the silvers. So when balancing net ionic equations, we need to look at and make sure that the law of conservation of mass holds true. So balancing out our elements as well as balancing out our charges. A net ionic equation shows only those particles involved in the reaction and is balanced with respect to both mass and charge. A net ionic equation shows only those particles involved in the reaction and is balanced with respect to both mass and charge. Single and double replacement reactions can have net ionic equations. So let's write and balance a net ionic equation. An aqueous solution of iron 3 chloride and potassium hydroxide are mixed. A precipitate of iron 3 hydroxide forms. identify the spectator ions, and write a balanced net ionic equation for the reaction. So our first step is going to be to write out our skeleton equation. So we have aqueous iron 3 chloride plus potassium hydroxide, and that is going to give us iron 3 hydroxide, which we know is our precipitate, so that's our solid, plus KCl. But remember, we need to make sure that we obey the law of conservation of mass. We need to add a 3 in front of our KCl and a 3 in front of our KOH to balance out this equation. So now we want to go to our ionic equation. So we're going to break up all our aqueous compounds into their ions. So we have Fe3 plus 3 Cl minus because of the subscript, plus 3K plus 3 OH minus, yields, remember that our solid stays together, plus 3 potassium ions plus 3 chloride ions. And so now our next step is to determine our spectator ions. So what do we see repeated on both sides? We see we have 3K plus and 3Cl minus on each side. And those are going to be our spectator ions. So we're going to cross those guys out. And now we can write our net ionic equation. We have Fe3 plus 3 OH minus yields FeOH. And that is our net ionic equation, because the iron 3 and the hydroxide ions are what participate in the chemical change. So let's predict the formation of a precipitate, and some combinations of solutions produce precipitates while others do not. Whether or not a precipitate forms depends upon the solubility of the new compounds that form. By using the general rules for solubility of ionic compounds, you can predict the formation of a precipitate. So here is our general solubility rules. So our salts of alkali metals and ammonia, they are soluble except for some lithium compounds. Our nitrate salts and chlorate salts are soluble, and there are a few exceptions there as well. Our sulfate salts are soluble, but compounds of lead, silver, mercury, barium, strontium, and calcium are not with sulfate. Chloride salts are soluble, except for when it is with silver and some compounds of mercury and lead. Carbonates, phosphates, chromates, sulfides, and hydroxides are mostly insoluble, and compounds of the alkali metals and of ammonia are soluble with carbonates, phosphates, chromates, sulfides, and hydroxides. So will a precipitate form when aqueous solutions of sodium carbonate and barium nitrate are mixed? So we have our equation here, and we can see that this is a double replacement reaction, and we need to determine the precipitate. We know that we're going to form sodium nitrate and barium carbonate, and if we look at those solubility rules that we just wrote down, we know that carbonates, the bottom row of the compound column, the carbonates are mostly insoluble, while nitrates are mostly soluble. So we can determine from those rules that the barium carbonate is going to be our solid, or our precipitate. So here we have our ionic equation, and now we need to identify our spectator ions. So we have sodium and the sodium, and we have our nitrates are crossing out, and these should be balanced out. And so there, now we can see that we are left with our net ionic equation. Carbonate plus barium yields our barium carbonate solid. So here we are balanced, we obey the law of conservation of mass, and our charges also cancel out. So in review, a net ionic equation shows only those particles involved in the reaction and is balanced with respect to mass and charge. By using the general rules for solubility of ionic compounds, you can predict the formation of a precipitate. As always, all information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchemistry.com. Have a good day, guys.